Yeah. Good morning, every one of you. So until the last class, we were seeing this gas absorption. In the gas absorption, we have covered so far all the topics which are there in the contents, like gas absorption, their definition, types of absorption, physical absorption and chemical absorption. Then stripping definition we have seen. Then industrial applications of absorption process. Then selection of what are the criteria to select the solvent for the absorption as well as stripping we have seen. Then absorption equipment in that and a very brief and a detailed way we have seen this packed columns. Okay, what is its design procedure and everything we have seen. Then various packings, regular packing or this random packing we have seen. Then what are the operational problems in the absorption column we have seen. Then tower packing, what is the required criteria to design the tower packing we have seen. Then HTTP method, then advantage of packet tower, then packing materials, what are the materials, advantage of tray columns. So then design procedure, then material balance, the general material balance, and this operating line equation we have derived, and how to determine the height of the packet tower. Among the two methods, we have used this mass transfer analysis, that is Z is equal to HTU into NTU method to derive our columns. Then this gas phase, all these derivations we have done. And I have given you for the assignment this liquid phase derivation you have to do, that is Z is equal to HTU into NTU. Then absorption in rich gases we have seen yesterday, all this derivation. So then the last topic which has been left is absorption with chemical reaction. So what is this absorption with chemical reaction? So far whatever we have seen previously, that is entirely a concerned about, they are concerned about absorption without chemical reaction. So without chemical reaction means it's just a physical absorption. So weak van der Waals forces will be involving there. So there is no much interaction between solute and the solvent there. But here the solute and solvent are having a strong bonds. Why? Because there is a chemical reaction. So because of this reason, so the absorption process will be taking place at very high rates and mass transfer coefficient will be very high. But whenever it is irreversible reaction, the solute cannot be separated from the solvent. So we cannot reuse the solvent and we cannot utilize the solute, separated solute also. That's the only disadvantage. But for many acidic gases removal, we will be preferring the basic solvents, and for the removal of many basic gases we will be preferring to remove with acidic solvents like this. So acid and base will have a strong interaction and they will be producing a neutralizing reaction. So the absorption followed by chemical reaction in liquid phase. So usually whatever the gas which is there in the solute which is there in the gas phase, which will be absorbed inside the liquid, and there in the liquid phase the reaction will take place. So this liquid phase is often used to get more complete removal of solute from a gas mixture. So if you want to remove the more complete removal of your solute from the gas phase, you have to use a absorption with chemical reaction. Then only it is possible. Otherwise, using the physical absorption, it is not possible. Majority of the solute will be coming in the gas outlet only. Then what is the example? So a dilute acid solution can be used to scrub ammonia from the gas stream, and basic solutions are used to remove carbon monoxide and other acidic gases like SO2, SO3, H2S. So all these are the acidic gases can be removed using some basic solutions, or acid solutions can be used to remove the basic gases like NH3. Then the reaction in the liquid phase reduces the equilibrium partial pressure of the solute over the solution, which greatly increases the driving force for mass transfer. If the driving force for the mass transfer increases, means it is proportional to the flux. So flux will be increased. Obviously, the mass transfer will take place at very high rates. So if the reaction is essentially irreversible at absorption conditions, the equilibrium partial pressure is 0 and NTU can be calculated just from the change in gas composition. So that is, if the equilibrium composition is 0, so then what happens? Obviously, the NTU equation will be reduced to 0. So for example, let us say this is absorption tower. So to provide an intimate contact between liquid and gas phases, we will be having this one. So first let us write, this is absorption with chemical reaction. With chemical reaction. Absorption with chemical reaction. So we are using the gas mass flow rate 0 and its solute composition as Y mole fraction or mole ratios. Then here also G and here also some Y. Okay, whatever we are preferring, whether 1 or 2, it doesn't matter. Now Why? Because we are not deriving anything here. So this is liquid which is entering counter current to this one. So composition of a solute composition of a liquid is X, and this also some solute composition of X. Usually due to this gas is there, that will be measured in pressures also. Okay, for the to measure the gas composition, it is very convenient to measure the pressures or a partial pressures. So P can be used. Usually the P star or PE we can say, or PE equilibrium partial pressure, P star or PE will be usually zero. Why? Because a large part of solute will be solubilized into the liquid. Why? Because there is a chemical bonding in between them because of formation of chemical reaction in between them. So the absorption followed by a chemical reaction usually takes place in the liquid phase, is often used to remove the complete removal. So complete removal of solute from the gas phase. So it is very much possible to remove the solute completely from the gas phase using the absorption with the chemical reaction. So the examples we have seen already, but what is the advantage here means the partial pressure or the mole fraction ye star or y star, it will also be zero. Why? Because P star is already zero. Under such conditions, the NTU equation we already know. We have derived for the lean gases and the this one lean gases as well as rich gases. So NTU is integral in between limits y2 to y1 dy by, this is also capital, this is also capital, y2 to y1 or capital or small, doesn't matter, for the both things same. Okay, then divided by I think y. Okay, y. So let us take that. Okay, so now what happens? Y minus ye. Y minus ye. This is the NTU equation for the lean gases we have seen. So this NTU equation, if the ye is already zero, then simply this will be reduced to NTU is equal to integral y2 to y1 dy by y simply. So this is equal to integral 1 by x dx is nothing but ln x, that is ln y here. In between limits y2 to y1. Therefore, upper limit minus lower limit is ln y1 minus ln y2. Therefore, ln a minus ln b is equal to, we can write a ln property ln a by b. So similarly, ln y1 divided by y2 is nothing but our NTU equation. For example, in the chemical absorption case, if the solvent is your if the solvent used is your HCl, dilute HCl you are using, and if your solute which is there in the gas phase is NH3. Okay, for this operation, since this is a basic gas, this is an acidic solution, the reaction between them will be a strong bonding reaction. Okay, that chemical reaction will take place, a neutralization reaction will take place. So because of this reason, if your NH3 concentration has been reducing from, for example, let us say 6 to 0.02%, means 6% in the entering gas and 0.02% in the outlet gas. Here 0.02% in the outlet gas. Then what happens? Y1 is equal to around 0.6%. 6% means 6 divided by 100, that is 0.06. Then y2 will be 0.02%, that is 0.02 divided by 100 further. So almost it is zero. It is reducing to much lower amount, that is 0.0002 is the percentage. Then if you substitute in this equation, NTU equation, then NTU is equal to ln y1 is 0.06, y2 is 0.0002. Therefore, if you calculate this one, you will get ln 300. So ln 300 you will get nearly 5.75 or something like that, 5.7 you can take. So similarly, the same process is physical absorption process. Under the physical absorption process, if this is a water, you are using water to separate out NH3. What happens? This NTU will be very high. Number of transfer units takes place for this operation. NH3 and H2O absorption process is very high. Why? Because there is no chemical bonding between water and this NH3. Only physical absorption will take place. That's why the NTU will come here using the experimental thing, that is around 12. Okay, almost the double of this one is required for this one. So the advantage of this absorption with chemical reaction is less number of transfer units are required. compared to the physical absorption case, which required more number of transfer units. So that's the advantage of that one. So that I have given in the PPT also here. So example, the absorption of NH3 in dilute HCl with a 300-fold reduction in gas concentration, that is 62.02%. So from this equation, if you calculate this one, ln y1 by y2, 5.7 you will get, which can be compared with NTU12 for the same change in the concentration using water at this condition. Under the same conditions, if you change the solvent from HCl, dilute HCl to your water, then it is a physical absorption. That's why the number of transfer units required will be very high. The efficiency will be very low because of the number of transfer units which are required very, very high. So further, if you see, the advantages are there further for the absorption plus reaction or absorption with chemical reaction. So what are the advantages? That one. So increased mass transfer coefficient due to this less number of NTU is one advantage. Less NTU is one advantage, and second advantage is your increased mass transfer coefficient. Increased mass transfer coefficient. So that because the concentration is fast, very fast, it is reducing from 6% to 0.002%. That's why. So your interfacial area offered will be very high. Due to the chemical bonding, your mass transfer coefficient will be very high. For example, same thing for the NH3 and this NH3 is solubilizing in H2SO4. Okay, that is also acid. So this NH3 is a gas, that is a basic gas. And if you operate this with H2SO4, what happens? Its KYA, mass transfer coefficient value, will be around 1.52. Whereas when you just use in place of H2SO4, in place of H2SO4, if you use water, its KYA, mass transfer coefficient value, will be 1.52 divided by 2. Means half of the mass transfer coefficient is reduced in case of H2O and NH3. Whereas if you use the acidic gas to separate this acidic liquid to separate the basic gas, its mass transfer coefficient is nearly 2 folds high or 2 times higher than the normal physical absorption process. Why? Because the gas film resistance is controlling. So gas film resistance is usually controlling the mass transfer process, and its effective area will be increased. Okay, because of that effective area, increased effective area, okay, or mass transfer area will be increased. If in case if the liquid film resistance is a dominant, so okay, as maybe in the case of CO2 and H2 removal, okay, like CO2 removal or H2O removal using some aqueous solution, whatever it may be, some ionic liquids or something like that, aqueous solution. So like, or we can say ethanolamine. Ethanolamine is one of the example to remove the CO2 gas. So H2 hydrogen gas. So the rapid chemical reaction in the liquid phase, which will be leading to a very large increase in the mass transfer. Even if it is a gas film controlling, so its mass transfer coefficient will be increased. Even if it's a liquid film controlling, then also its mass transfer coefficient is increased. Due to this increase in mass transfer coefficient, its effective interfacial area will be very much increased. Due to this effective interfacial area increase, the mass transfer coefficient is also obviously produced will be nearly 2 folds higher than the normal one. So the same thing is given in PPT also. You can read. So the further advantage of absorption phase reaction, that is chemical absorption, is the increase in the mass transfer coefficient. So some of this increase comes from the greater effective interfacial area, since absorption can now take place in the nearly stagnant region, that is a static holdup as well as the dynamic liquid holdup. So for NH3 absorption in H2SO4 solution, the KGA was 1.5 to 2 times, okay, nearly 1.5 to 2 times the value of your absorption in water, okay, compared to the absorption in water, NH3 absorption in water, the mass transfer coefficient will be 2 times greater than the absorption of NH3 in H2SO4. So since the gas film control resistance is controlling, this effect must be due mainly to the increase in the effective area. So because of this gas film controlling, this increased mass transfer coefficient, everything is due to the effective area, increased effective area. When the liquid film resistance is dominant, as in the absorption of CO2 and H2S in aqueous solutions. So like ethanolamine, a rapid chemical reaction in the liquid can lead to a very large increase in the mass transfer coefficient. So even it is liquid film resistance controlling or the gas film resistance controlling, with the both, the mass transfer coefficient will be very high. So when absorption is accompanied by very slow reaction, so it is accompanied by very slow reaction, the apparent value of Ka, so this is not Ca, this is Kya, okay, maybe lower with the absorption alone. So as an example, if you take the chlorine in water followed by hydrolysis of dissolved chlorine, the slow hydrolysis reaction essentially control the overall rate of absorption. Okay, that is about absorption with chemical reaction, whose advantage in increasing mass transfer coefficient, increasing interfacial area, and also decreasing the NTU. So all these are the advantages which are offered by chemical reaction. But only disadvantage is whenever it is irreversible reaction, we cannot separate out solute from the solvent, so that we cannot use the solvent once again for the next cycles, and also we cannot utilize the solute as such, okay, for other purposes. So that's the disadvantage. Is that clear?
Yes, sir.
Okay, so usually the equipments which are required for this particular operation, absorption with chemical reaction, is only two types of equipments we can use. First one is a co-current flow operation. So what is this co-current flow operation? Why we have to use the co-current operation? We have to see that one. So here what we are doing, it's a counter current operation. So for example, let us see CO2, which is a gas, which is entering from the bottom and traveling to the top. But whereas the liquid, the aqueous solution or ethanolamine, which is entering from the top and it is traveling from top to bottom. So NTU under this condition, for example, let us say counter current. So co-current means the same tower will be there once again. The gas will also be entering at the same bottom to top, or liquid will be entering from the bottom to top. This is a counter current. Under this condition, NTU, this is co-current. This is co-current NTU. If you operate the column using the counter current, or if you operate the column using the co-current also, then your NTU co-current will be nearly equal to your NTU counter current. So there is a same NTU will be produced in the co-current as well as the counter current whenever the absorption with chemical reaction takes place. Okay, that's the usual process in this absorption with chemical reaction. But the co-current will offer a advantage. So what is that advantage? Means there is no flooding limitations, and also the gas flow rate we can maintain much higher than the normal rate we can maintain, and this will reduce the column diameter, and the corresponding increase in liquid and gas mass transfer velocity gives higher mass transfer coefficient. So in the co-current, rather than using the counter current for the absorption with chemical reaction, if we can use the co-current, NTU will not have any change in effect, but they will offer an advantage, like they will increase the mass transfer coefficient, and we can able to maintain high gas flow rate, okay, high gas flow rate as well as high liquid flow rate also we can able to maintain very high compared to the normal conditions. And there is no flooding also, in the co-current operation of your absorption with this particular reaction. Okay, especially this is valid only for absorption with chemical reaction, not for the physical absorption or other cases. With absorption without chemical reaction, it is not possible. It is very good to use the counter current only, absorption without chemical reaction. Especially in the case of absorption with chemical reaction, we can use this following co-current operation. Why? Because the NTU will not have any effect, but the mass transfer coefficient will be increased, and high gas rates and liquid rates can be maintained, and therefore mass transfer coefficient increase, and there is no flooding conditions also effective in this co-current operation. So that's the advantage of your using co-current flow operation. So when the chemical reaction is essentially irreversible and the equilibrium partial pressure of the solute is zero, the number of transfer units for a given separation is same for counter current operation or for co-current flow of the liquid and gas. So the advantage of co-current operation is that there is no flooding limitation, and a gas flow rate much higher than the normal can be used. And this reduces the required column diameter, and the corresponding increase in liquid and gas mass velocity gives high mass transfer coefficient. So this, as such, the liquid rates as high as 50,000 to 1 lakh lb per feet square hour can be maintained, can be used in this particular co-current operation. And the value of kGa, which is mass transfer coefficient into interfacial area, or the HTU, can be estimated approximately by extrapolating counter flow data for the same system to the higher mass velocities. So this was eliminating majority of the limitations and offering the advantage whenever you are using co-current operation rather than the counter current operation, which is preferable in absorption without chemical reaction. Okay, is that clear? This co-current flow operation, why it is advantage?
Yes, sir.
Okay, then next is the last topic. This is same absorption with chemical reaction, which can be carried out in the absorption in tanks. Okay, generally in tanks. What happens in the absorption with chemical reaction, which is carried out in tanks? So there will be a dispersion. So gas bubbles will be dispersed into the liquid phase. Okay, the liquid is mixed by an agitator or by a gas bubbles. We can mix this liquid themselves, and there may be an appreciable back mixing of the gas. So this tends to lower the conversion. So as you can see in the lagoons, in the water treatment plants, aeration process, what happens in the aeration process? Majority of your BOD or the organic matter which is there inside can be removed by oxidation process. So how that we are oxidizing? We can supply the proper air. We can supply the oxygen to that one. We can supply the oxygen using some aeration tools, aeration or air lagoons, we can say. Okay, like paddles or lagoons, we can just rotate this liquid so that whatever the BOD, oxygen matter, biological oxygen demanding matter, organic matter is there, which will be broken down into the small molecules, and we can separate out the pollutants from that one. So that is the best example. That is the aeration process, you can say. So these two equipments are popularly used for absorption with chemical reaction. Especially this aeration process is for the treatment of activated sludge process. Okay, for the treatment of activated sludge, we can use, or the breakdown of organic waste, we can use this particular absorption in tanks. Okay, I hope it is clear.
Yes, sir.
Okay, yeah. So far this unit 1 has been completed. If you have any doubts, you can just ask me. Otherwise, I will quickly revise whatever the topics so far we have covered in the unit 1. Then we will start from the next class, unit 2. Okay, yeah, please go ahead if you have any doubts, or people who have done the assignment, they can tell me that they have completed the assignment. That is liquid phase Z we have to calculate.